My name is Konrad Domanski. I'm from Fluxim, and today I will talk about the performance of perovskite solar cells under simulated outdoor conditions, but we did everything in the lab. So I showed this slide last year how research in PV is a little bit like climbing the Matterhorn, our beloved Swiss Matterhorn, the Toblerone mountain. So if you look at this mountain from the map, which is the iconic view you see on postcards, you see three routes to the top. There is the Horny Ridge. This is the easiest one, the first one to be climbed, the one everyone was racing to climb at the beginning. And it's a little bit like efficiency. Then once the Horny Ridge was climbed, everyone's eyes were on the north face. This is a 1 kilometer sheer face of granite and ice. Really difficult to climb, but everyone was trying. Eventually it was climbed, and this is a little bit like stability. I think we're still somewhere on this wall, working our way up. And then in the shadow, there is the east face. It's also a very difficult route, only attempted by real professionals. But it's neither the easiest, neither the most prized one to climb. And people don't attempt it very often. And it's a little bit like the upscaling end or the cost. And to make things harder, it has to be climbed down. But even if you could freeze conditions during the day of the climb, the conditions are different at different stages of the mountain. So you would start with moderately high temperatures, with slow winds, a little bit of UV light, and as you make your way up the mountain, the conditions change. The temperature drops, the UV becomes harsher, and you get higher gusts of winds. And it's a little bit like the solar cells, because they also experience variable conditions throughout the day. But at the end of the day, it's only the energy used that matters. So with that in mind, we modified our setup with PSC that could already very low temperature illumination atmosphere to also do condition cycling. And we used our workhorse device with FTO, titanium peroxide spiral gold, which gives us good efficiency, good reproducibility, and behaves nicely at room temperature at maximum power point. And in this study, we only use non-encapsulated devices. So what we did at the beginning is we explored the parameter space of temperature and illumination. And we looked how perovskite compared to silicon heterojunction cell, which was fabricated on N-type wafer, fully textured, how they behave across this parameter space. So we see for the silicon, as we go with lower temperatures and higher illumination, at least to some extent, we increase our efficiency. For perovskite, we could only find the trend with illumination, and we didn't find one for temperature. But then the question was how they behave at maximum power point, because this is where we actually operate ourselves throughout the day. So we looked at the voltage at maximum power point, and for silicon, again, we see that it gets higher towards lower temperature and higher illuminations, up to around half the sun. For perovskite, again, the trend is the same as for efficiency. It gets better only with illumination. And then for the current, it behaves a little bit differently. Here we already normalized the current for the irradiance that the cells show. And we see only a slight decrease by going towards lower illumination, but actually this is pretty small, and they behave linearly together, which is nice for tandem devices if you think about it. Because once you match the current to the tandems, they remain matched regardless of the temperature of the device, and they also behave linearly with irradiance. So that's a good news for tandems of those devices. So here I plotted the temperature effect on the efficiency a bit differently, and for silicon, you see that we get those negative temperature coefficients of 0.2, 0.25% per Kelvin, which is what you would expect for a silicon heterojunction device. It's higher for PERC or more standard silicon devices. For perovskite, we didn't find anything, which is again a rather nice message because you would expect anything to drop. So we lose a little bit of VOC, but we compensate with higher fill factor. Probably because we have spiral ohmicap there, the transfer becomes better as you heat up the device because the hopping transport, so you gain a little bit of fill factor, which you lose in VOC. So we did that pre-characterization to see how our devices behave across this parameter space. And now it was the time to subject it to some real temperature illumination profiles. So what we did is we handpicked two most extreme days in terms of illumination and temperature from each month between April 2016 and May 2017. This is how the profile looks like, and we subjected both silicon heterojunction and perovskite cells, which were sitting inside the same holder, the sample holder. We subjected them to those conditions. And here you see the average efficiency on a given day of the devices, and we see that silicon behaves best, or the efficiency is best, in the morning and in the evening, because during the middle of the day, the temperature kicks in and we lose the voltage. For perovskite, the story is really different. We see they behave best in the morning and don't really recover towards the evening. And this is because of reversible degradations. As the samples get illuminated, they start losing efficiency. We just saw several examples of that. And we also see that there is a monotonic trend towards decrease in efficiency. So early warning about the degradation, permanent degradation. So this is how the energy was distributed across our data. Here you see temperature and intensity, and we see that most energy is generated within this region. So now the question is how our cells respond to that region. So for silicon, we see that most energy, again, is generated in this region. That's what we would expect. This is where most energy is shown on the device. However, the cells are most efficient in this region. So there is a slight mismatch. But okay. For perovskite, the story is a little bit more positive. Again, most energy is generated here, and the cells are also most efficient here. So that's a good match. That's what you would like. So then let's look a little bit at the degradation. Because we did this initial characterization, we could predict how efficient our cell would be on each day, on average, because we know how it will respond to different temperature and illumination. So we plot here the blue curve, the difference between what we generated and what we expected to generate at the beginning. So for silicon, you see that sometimes we generate a little bit less, sometimes more, no monotonic trend. For perovskite, the story is again different. We see that we consistently generate less and less as the experiment progresses. So we see some degradation. So here I plotted a table. This is how efficient our devices were at the beginning. This is what we measured under standard test conditions, under 1 sun 25 degrees. This is what everyone measured. This is what we predicted to be the average efficiency across the entire experiment, again, by using this data. So we see that it's a little bit higher for both cells. This is how much energy was incident on the devices, and this is how much energy they generated. And now the measured efficiency across the entire experiment was very close to the predicted one for silicon, and 2% lower for perovskite. And so we see that it's 100% one of what we expected from standard test conditions for silicon, and only 91 for perovskite. So here we see that the standard test conditions are actually a very good predictor of how much energy you can expect from your silicon device, but not so much for perovskite because of the degradation effect. And this is when we compare to the predicted efficiency, which is this one, and we see that we get even better match for silicon and even worse for perovskite. So let's have a look at like one day. I just chose one day the temperature illumination profile for both devices. And what you can see here, the orange curve is perovskite, the blue one is silicon heterojunction. The broken curves are what we would predict the efficiency to be on a day at any given moment. Again, from this pre-characterization colorful graph that I just showed you. And the solid line is what we actually got. So we see that for perovskite, we developed this discrepancy towards the end of the day. This is the reversible degradation that we see kicking in. But there is always at some point of a day, a point where we get pretty close, or like closest to the predicted efficiency. And what we did, we looked at this point every day and quantified how much of the degradation is recovered and how much is actually thrown. So this is how the result looks like. The orange is reversible degradation, the blue is irreversible, and we see that for the perovskite device, we consistently increase we accumulate the irreversible degradation. So before I conclude my talk, I would like to do a little bit of advertising. Over the past year, I put this setup that I developed at EFL, or the concept of it, into a more compact form factor. This is Litos, which was just released by Fluxim. We can do maximum power tracking, constant current, constant voltage, across 32 parallel channels. We can control temperatures between -10 and 125 degrees with white and UV illumination up to 10 suns for accelerated aging experiments. We can control the atmosphere, and we wrap it up in nice, professionally developed software to automate all the measurements. We also offer extensive customer support to help you set it up and run experiments. And we sell this with solar cell, OLED, and a hybrid version. And if you know our other tool, Paios, you can connect Paios to Litos to, for example, every morning measure impedance spectroscopy or measure IAPS every 2 days for every channel of Litos. But the two instruments are also completely standalone. And let me conclude, we investigated perovskite solar cells under real indoor-outdoor conditions, if I could say so. And we compared the energy yields with silicon heterojunction. So we established a method to use any arbitrary illumination temperature profiles from anywhere in the world without physical presence outdoors and simulate it in the lab. We see little temperature dependence for perovskite solar cells, unlike for silicon. Silicon and perovskite are a good tandem pair because once you match the currents, they remain matched. Although I have to say we didn't look at the spectral variations throughout the day in the study, I have to give you that. And we see reversible and irreversible effects in perovskite solar cells. And finally, Fluxim just released a tool to help perovskite and OPV researchers measure stability. And with that, I would like to help the team at Fluxim, as well as the team at EFL, especially Dr. Logan Tress, who actually led this study, and let me present it here for you. And of course, you for your attention, and I'm happy to answer questions. Thank you very much.
Thank you for your presentation. I wondered, basically, as you're saying that the perovskites have a better match between irradiant or outside weather conditions and top performance. Did you also do some calculation, assuming there would be no degradation, what PCE for perovskite you would need to match the yield of silicon? Because in principle, that should be lower.
Well, I don't know if it's fast enough to go basically on table. So if there was no degradation, this is what we would predict from this drug pre-factorization experiment. So compared to the standard test condition, we would expect just a little bit higher efficiency on average if there was no degradation. So if you wanted to match the silicon, well, this is 21.3 under standard test conditions, you would need probably 21.3 for perovskite to have the same energy yield. Yes?
Thanks so much for your presentation. Short question, I shout or you leave it in the internet? Okay, I'll shout. So you investigated the cells on the 50 degc, and with a little bit of imagination, one can see a bow in the data of the perovskite. So did you dare to check what happens above 50 degc on the temperature stability?
So we know pretty well what happens. They degrade with a different mechanism. They degrade through gold electrode reacting with perovskite. So in this study, we actually were careful not to go to that temperature because, well, we would compromise all the conclusions of the study if we finally, if it once activated another mechanism of degradation. And, well, what you actually see in our profile we never go beyond 50 degrees. This is the slope curve temperature. In our data, and this is data from close to Lausanne, this 50 degrees is the highest we hit, and -9 I think was the lowest data point in our data set.
So for South Europe and Africa, we make a new study. Or a different device architecture.
Of course, and if you want to put it on top of Mount Everest, you would need another one again.
Yes.
With different range.